everyone, my name is Wei Su. Today I'm going to talk about our work, supporting transactions for bulk NFSv4 compounds. First, I'll provide a general idea of what motivated our work. NFSv4 introduced compounds to amortize network latency. In order to utilize the full power of compounding, we should pack as many operations as possible in one larger compound, as is shown in this figure of writing multiple files at once. To write files, we should first use lookups to navigate the current working directory, and then open, write, and close the files. Thanks to compounding, we can issue these operations all at once to the server and only have to pay one round-trip latency. A previous work in our lab called VNFS is a solution that provides a set of vectorized I/O APIs to allow operating multiple files at one time and translates vectorized operations to larger compounds. We evaluated the performance of VNFS against the vanilla NFSv4 client. Results show that VNFS can accelerate applications by from 2.5 times to 259 times. So NFSv4 introduced compounds to improve I/O throughput. When it's fully utilized, compounding can accelerate applications by as much as 2 orders of magnitude. However, this poses a challenge to error handling of applications because NFSv4 doesn't roll back incomplete compound executions. If an operation in a compound fails midway, the NFSv4 server will stop executing this compound and report the error status, but the previously succeeded operations are left as is. Besides, if the server crashes while executing the compound, no recovery will be performed when the server restarts. Therefore, the client application would have a hard time handling these exceptions because any operation can fail and crash can occur anytime. So it's difficult for the client to figure out which operations to revert in order to restore the file system into the initial state. Therefore, we developed Tcnfs to add transaction support to NFSv4 compounds. With transactional compounds, the server provides atomicity and applications would only have to reissue the compound if it failed. Now I'll discuss the design and architecture of Tcnfs. First, we expect that the client is vectorized so that compounding would be fully utilized and transaction would make more sense. In our Tcnfs server, the transaction layer provides transaction semantic support for compound execution. When a compound request reaches the Tcnfs server, the transaction layer serializes and commits it into the transactional metadata database as a recovery record. Then it creates backups for the data blocks that will be changed by the compound. Next, it executes the compound operations. And finally, after compound execution ends, it removes the backup data as well as the recovery record. If an error occurred during compound executions, Tcnfs will reverse the previously succeeded operations. If the server crashes while executing the compound, the recovery record will not be removed. So when it restarts, it will detect this and parse the recovery record to retrieve the compound request, and then reverses the partially executed compound. We developed a prototype of Tcnfs based on NFS Ganesha, and here is our architecture. In the transaction layer, there are 4 components. The log manager coordinates conflicting access from multiple clients. The backup manager creates and cleans up backups. The undo executor reverses partially executed compounds due to failure. The metadata translator maintains a mapping between NFS file handle and the local file handle given by the underlying file systems. The transaction logger creates and removes the recovery records. The offline undo executor reverses partially executed compounds resulted from crash. We used copy on write enabled file systems such as XFS and BTRFS to reduce I/O throughput overhead by avoiding unnecessary data copy. We also used an SSD with power loss protection to ensure durability and reduce F-sync latency. In this section, I'll present some interesting performance numbers. Here's our experimental setup. We used 3 identical machines. One machine acts as a server and has a 200 gigabytes of SSD for the backend storage of Tcnfs. The other two are client machines running a total of 8 client virtual machines. For the micro benchmark, we ran the write files workloads, in which the clients wrote 1,000 equal-sized files continuously for 30 seconds, and we measure the throughput. We vary the file sizes from 1K to 16 megabytes and the number of clients from 1 to 8. We didn't inject any additional latency, so the RTT was 0.2 milliseconds. The relative throughput is the ratio of throughput on TC-NFS to that on vanilla NFSv4 server. We can see that for large files of sizes over 256 kilobytes, the overhead was small and less than 20%. However, for smaller files, the overhead went from 36% to 26 times. The smaller the files and the more the clients there were, the overhead was larger. The overhead was so high, and we would like to know what caused such huge overhead. To find out the reason, we simulated the write files workload locally by writing 1,000 equal-sized files to the SSD in parallel using 1 to 8 threads, and then we measured the throughput. There were two types of workloads. One was interleaving backup, which emulated Tcnfs by creating backups using copy and write feature in XFS before each write. The other was no backup, which emulated vanilla NFSv4 and didn't create backups. The results are shown in this figure. The no backup workloads scaled well with more threads, while the interleaving backup couldn't scale and sometimes became worse. When there were 8 threads, throughputs were lower than the one-thread scenario. This figure explains the high overhead of Tcnfs for small files and multiple clients. As no backup scaled well and the interleaving backup went worse, the overhead of interleaving backup would become very high. So now we can confirm that it is the copy and write operation in XFS that limits the scalability of throughput and causes the huge overhead of small file and multi-client writes. We also tried other copy and write enabled file systems such as BTRFS, but the throughputs were even lower, and we found that XFS was actually the best one. We also performed some macro benchmarks using real-world applications. We experimented with query utils by recursively listing, copying, removing, and symbolic linking the Linux kernel source tree. In these benchmarks, we used a single client and varied network latencies. Results showed that the overhead of Tcnfs for real-world applications is modest, and as the latency increases, the overhead drops significantly. When the latency was 30 milliseconds, all these workloads showed less than 10% overhead. Although when the latency was 0.2 milliseconds, the overhead could be as high as 35 to 50%. And Tcnfs with VNFS was still much faster than the traditional NFSv4 system, considering the magnitude scale improvement of VNFS. So finally, let's come to the conclusion. In this work, we built the TC-NFS system, providing transactional ACID semantics for NFSv4 compounds. This greatly reduced the error handling burden of client applications. Currently, our prototype supports transaction semantics for open, create, write, link, and remove. We also support rename for regular files. In the future, we'll add transaction support for more mutating NFS operations. Tcnfs introduces modest overhead to single-client real-world applications. Considering the huge performance improvement that a vectorized NFS client can offer, applications on Tcnfs can still enjoy performance boosts. The overhead was high on multi-client workloads, but we have found that the root cause was the copy and write along with fsync was slow on XFS, and we believe that it will be resolved once the copy and write feature is optimized in the future. That's the end of my presentation. Thanks for listening. Please follow the links for more detailed design and experiments.
So Brian Kim asks, first, mentions that this is very interesting work. It makes sense that the backup for small files in Tcnfs causes significant overhead. What kind of solutions are you exploring to mitigate this overhead for small files?
Thank you for your question. So, unfortunately, in this work, where we couldn't find any workaround or solutions to reduce such overhead because we have found the root cause was in the underlying file system. So we will look into this problem and try to optimize the underlying file systems in the future.
Okay, thank you. So we have another question from Sahibir. He says, in SSD non-flash memory, there is no physical possibility for copy on write because you cannot write in place. What happens if redirect is redirect on write even if you don't request it? So the question is, could that affect the results because the software is doing funny things to emulate copy on write? I think that
Mm, I
perhaps to frame this as a more general question, how would your results depend on the backend storage of NFS? This is
yeah, I think that's a very good question. Um, it's true that in like raw flash chips, it's not possible to write in place, but for SSD products, there are translation layer that can make this device compatible and works like a regular block device. So um, I think it is it is not a problem like not being able to write in place because for example, I think if one tries to doing a copy on write operation by using reflink, IOCT or system call, the underlying file system should just record like fork this block or create a link to this block to another file, and only when another operation is trying to override this block, then the underlying file system should write a new block. So I don't think this should affect the performance or cause any additional overhead.
Okay,
Yeah.
thank you. And we have time for one last small question from Michael Factor, who enjoyed your talk. He said he's curious if you considered roll forward as opposed to rollback approach.
Mm, Not really. We didn't consider the roll forward, and also because we think rolling back is more convenient to like recover or reverse previously succeeded operations because the NFS server will execute the operations in a compound in the forward order. So we believe that it's quite natural to reverse it in the rollback or reverse order.
So I think we have 1 minute for one more question that I
Yeah.
wanted to ask. It's not surprising that transaction support adds overheads to NFS.
Yeah.
My question is, if you have any intuition or if you looked at the comparison between this overhead and the overhead that any application side transaction support would add. So would it be possible to remove transaction support from the application side and just rely on the NFS, on the compound NFS transaction support?
I think the assumption of this work is that the applications doesn't implement any transaction. So without transaction, they will suffer from error handling problems. So therefore, we, the NFS server, will provide transaction semantics so that the applications won't have to implement transaction, which is complex for small programs like Corutos. So I think for larger applications like database, which already comes with transaction support, they can just disable the transaction support so they don't have to take this overhead.
Okay, that sounds great. So thank you again. And it's
You're
time
welcome.